All right, good evening, gentlemen. Let's get started. All right, so yesterday we looked at this circuit. We tried to determine the impedance and admittance parameters from first principles. Of course, for Z11, we calculated that to be 38/7. For Z21, we found that to be 4/7. All right. And then we looked at the other port. Again, looking from the other port, from port 2, we saw that the network was symmetrical. And so the transfer impedances were equal, and the input and output impedances were equal. So our matrix was found to be 1/7, 38, 4, 4, 38. I'm assuming that you took the time to review this. And so if you have questions about it, I'll answer them now. All right. We then went on to the admittance parameters for Y11. And of course, to do that, we short-circuited the port, yes? Y11, we found ZT looking in and then found the reciprocal, all right? So Y11 is 19/102. And for Y21, yes, what we did was the Y21, of course, with the I2 over V1 with V20. Okay, so it's the same circuit that we had before. Now, with the short circuit here, it means that the 2 and the 4 are in parallel. Of course, we saw that from the resistance equation. So it means that in finding Vx and Vy, we are first finding the voltage division between 4. Sorry, let me clear that. Between 4 and 26/19. And then, so that will give us Vx, and then between 3 and 4/3 for Vy. So that's what we did. All right, so the 26/19, and then 3 and 4/3. All right, so once we found Vy, yes, then we can find I2, which of course would be going in the opposite direction to the flow of the current, so it will be negative. So we get -2/102. Again, symmetrical network, and so the parameters, the Y parameters, 1/102, 19 -2, -2, 19. All right? So this is where we stopped yesterday. Does anyone, having gone through it, do you have any questions? All right, so we'll proceed. What if, however, looking back at the circuit, what if we were to split the circuit in two? So going back to the original, this is our original circuit. What if I was to split the circuit down the middle? So I'll have 4, 2, and of course 3/2. Right, so I'll have two resistances here. Right, 1.5, 1.5. Good. Which is what we have done here. All right. And what I want to do is to find the transmission parameters, because if I then put the other 1.5 here, and then we had 2, and then the 4 ohm. All right, you agree with me that if I were to connect these, that I'll get back the original circuit, because adding these two, we'll get our 3 ohm. All right, this being 2, that being 4. So if I split the circuit into these two and then connect them in cascade, right? Meaning the output of one at one port is the input for the other port, right? That's what cascade means, right? If we did that and then find the transmission parameters, no? So let's try that. So the equations for the transmission parameters, we recall it's the input voltage and current with respect to the output voltage and current. All right, that's for the transmission. So we're going to find the ABCD parameters of the network shown. So let's get cracking. So for this network, A is the relationship between V1 and V2. Yes, with I2 being equal to 0. Now, with I2 being equal to 0, what it is saying is that this port is open circuited. So in other words, if that is open, then V2 is the voltage seen across the 2 ohm resistor, since no current will be passing through the 1.5. All right. And with respect to V1, the current, the voltage, what's wrong with me today? The voltage across the 2 ohm resistor would then be found by voltage division. So V2 with respect to V1 would be equal to 2V1 over 4 plus 2. So 2V1 over 6. But what we are interested in is V1 over V2 for A. So it means that A, this implies that A is equal to 3. Is everybody comfortable with that?
Yes, sir.
Okay. Now, since I have the open circuit, I can go ahead and find C. All right, since I2 is 0, I can just go ahead and find C. And C would be equal to I1 over V2 with I2 being equal to 0. All right. So again, if we look at I1 will be the current passing through here, since I2 is 0, yes? So V2, based on what we have here, will be 2I1. All right? So it means that I1 over V2 would be equal to 1/2. So I now found C, I have A, I know short circuit the port 2, and of course short circuiting port 2, we're making V2 0. So we're making V2 0. So you can, let's just go back to the circuit, make sure that we see what is happening. So I'm now making this short circuited. And for B, Yes. B is equal to V1 over minus I2. So the question is, what component, with this short circuited, what component of V1 would be seen across the 1.5? Now with the short circuit, it means that these two are in parallel. So I would need to find the voltage across that parallel branch. Yes? And once I find that, then I can find the current through the 1.5 ohm. So that's how we're going to find B. So let's look at that. So B is equal to V1 over minus I2. So it is 2 in parallel with 3 over 3.5. Right? Gives us 6 over 7. So the voltage across the 2 ohm resistor. Hold on, let's make sure. Look back at the circuit. What did we have there? Oh, I'm looking in the incorrect direction. Okay. So the voltage over the voltage across the 2 ohm, right? We're using voltage division. So it is a 2 in parallel with the 1.5. That is what. So it's 2 in parallel with 1.5. So this shouldn't be parallel here. Do you see the error? Am I speaking to myself?
No, yes, I know.
Go back to the circuit. Go back to the circuit. All right? We're trying to find a single resistance for these two. So it is 2 in parallel with 1.5.
Right.
And that gives me 3 over 3.5.
Yes, sir.
The error on the slide is that this is supposed to be 2 in parallel with 1.5, which is equal to 3 over 3.5. All right? Which is equal to 6 over 7. And for the voltage division, we're now dividing it between 4 and 6 over 7. Everybody with me?
Yes, sir.
Yes, sir. Using voltage divider.
Yeah, okay. So I2 minus I2 will be the voltage across the 2 ohm, yes, which is also across the 1.5. So it is this divided by 1.5. All right? So it's the voltage across the 2 ohm divided by 1.5, which gives us 4 over 34. So B, or D rather, no, B would be 17 over 2. Mr. Humphrey had a question?
No, sir.
Okay. All right, for D, we have that being equal to I1 over minus I2 with V2 equals 0. Again, we look back at the circuit. We want to find the relationship between I1 and I2. And as you can see, I1 would come to this node. So we're using current divider. Yes. So what we're interested in is the current flowing through the 1.5. So for D, we're using current division. So that's 2I1 over 2 plus 1.5. Which gives us 7 over 4. So D is 7 over 4. So our parameters for the first half of the network we're finished with this. So the transmission parameters for network A three, 17 over 2, a half, and 7 over 4. Now, the other half of the circuit, because remember we split it in two, eh? So if we look at the other half of the circuit, and we have to take it in the same, we have to maintain the same direction. So we couldn't turn this around to have 4 to 1.5. We now have to maintain the 1.5, the 2, and the 4 in that order. But, you know, there are some things that you can pull from this, but I am going to go through the entire analysis for your benefit. So here we have A to be equal to V1 over V2, just as before, with I2 being equal to 0. And that would give us the 1.5 V1 over V2, sorry. Again, V2 would be across the 2 ohm, yes? So we're using voltage division. So we have 2V1 over 2 plus 1.5. Give us 7 over 4. All right. For C, and please note, usual practice. If we're looking at the impedance or admittance, we normally do Y11, then 21, Z11, then Z21. In this case, we are doing A, then C, because the port, the second port, would either have the short circuit or the open circuit for both parameters. So C, I1 over V2 with I2 equals 0. So V2 is equal to 2I1, and so C is a half, as before. So yes?
For this, sir, I don't see how
I'm not hearing you clearly, Mr. Adams.
yes, sir. For A, sir, for the previous one, A, while I was just going through, I don't see how you get the 3.5 since
We're doing voltage division between 1.5 and 2.
I2 is a short circuited I1.
I2 is 0, so it's open
Oh, okay.
circuited.
I did I1 as open. Thank you.
All right. And then for B, again, you look back at the circuit. We have 2 in parallel with 4. Remember, the objective is to then do the voltage division between the series resistor and the combination of the 2 that are in parallel. So in doing this, so remember, this now would be the combination of the 2 resistances, but we're finding the voltage across the 2 ohm. But we are not doing voltage division between 1.5 and 2. What we're doing is voltage division between 1.5 and the rest of the circuit. But that would give me the voltage across the 2 ohm. All right, because the 2 and the 4 are in parallel. So we get this for that voltage, from which we then find the current through the 4 ohm. So we divide this by 4. So in dividing this by 4, we get 2 over 17. Kind of look familiar, eh? Which means, therefore, that B is 17 over 2. And then lastly, we find D, which is I1 over I2, V2 equals 0. So again, I short circuit the port with the 4 ohm. I then have the 2 and the 4 in parallel. All right? So we'll have current division between 2 and 4. And so we get D to be equal to 3. Now, of course, you can see that there's a pattern. So we have B and C remaining the same, yes? But of course, A and B are interchanged. Now, I don't want you to try and rely on spotting these relationships. I want you to be able to do the calculations from scratch, eh? All right. So we therefore have our TB. And so the transmission parameters for the combined circuit would be the product of these 2 matrices. So we have T to be equal to TA plus T times TB. We multiply them, and we end up with that matrix. Of course, you can put the fractions, right? So what do I want it to do for me now? I want you to take 5 minutes. Now that we have T, and remember, we have just done this from first principles, yes? So I want you to know, use the T and find the Y by using the conversion matrix. And also find the Z parameters using the same matrix. All right, so do that for me, please.
Sorry, sir. You said the Z parameters on which one?
Y and Z.
Y and Z. Okay, thanks.
Yes, sir.
Okay, so let's start. All right, were you able to confirm the values?
Yes, sir.
Okay, good. What did you get for delta? Delta T?
1.
1.
I can confirm that it's 1, sir.
1.
1, sir.
So that's the matrix that we'll be using. And so delta T being equal to 1, we have minus 1 over 51, 9.5 over 51 would of course be 19 over 102. Yes? So we have 19 over 102, 19 over 102. I hope you didn't bother to go to fractions, right? I hope you didn't, but I mean to decimals. But I really need to go and leave, you know. Anyway. All right, so we see that confirms OY. And of course, we can do the same with our Z. All right, just cleaning up the matrix, we get back the same Z matrix. All right, so in a sense, what we're saying is that depending on how complex the network looks, you can break it down into series, parallel, or cascade connections and use the appropriate parameters to simplify or to determine the overall set of parameters. And I have been hinting at it. I hope it is now solidly in your mind that this is how we build complex systems. So I can have, if I'm intending on building a large system, I simply break it up into blocks. And based on how they are connected, then I will know how to treat with the parameters that define individual blocks. If I don't have, if they are in parallel, for example, and what I have are the transmission parameters, no problem. I simply convert them to the admittance parameters, add them, and then if that combined system is then connected in cascade, I find the transmission for the combined system, and then cascade it with the other stage. All right, but that's how we build out complex systems. All right, now, of course, you can see that this circuit is quite similar to what we just looked at. Yeah. Now, let me hear from you based on what we have just done. Here's the question. All right, let me hear your approach. And I'm not saying whether or not you're right or wrong. There are not many of us in the room this evening. There are only 30. Let's start with Mr. Blackwood. Let me start with Mr. Blackwood. tell me what your approach would be.
So I'll probably break it in three.
But
You know what?
so Blackwood, we need to hear you, you know.
Sir?
I need to hear you. We weren't hearing you.
Oh, I was saying that I'll probably come up with three cascade connection.
Why?
Well, I'm a bit uncertain of how the 6 was keyed. I drawn the class late. But at the end, I can see that if I use the 4, 7, and 5, it's similar to the other one at the end. So
So
finding
what?
the parameter for that one would actually give me the other one.
Okay. How about you, Mr. Beckford?
I break it into two, and right where the 6 is, and then seen as they're both symmetrical. If I find
What is symmetrical?
when I break the circuit in two, if I break it in two,
At what point?
right at the 6, if I split the 6,
So if I split the 6, you're saying it makes it symmetrical?
hold on.
No, sir.
Hmm?
If I split
No, sir.
if I split it at the 6, if I split it at the 6, when I split one side and work it out, it would just be like if I split at the 6 and work it out, it would be like the mirror of the next network B.
Go again?
If I split it at the 6 and I have
Mhm.
network A on the left and network B on the right.
Mhm.
Network B would just be the mirror of network A.
So will that help us? How will that help you?
So sir, we could have just work out what we need to work out the network A and based on the configuration, we know what is what, so we can just
What configuration?
reveal that
What configuration are you referring to?
when I split the network and seeing that is the mirror of each other.
Yes, and I'm asking, you have said that it is the mirror of it. And I'm asking, what's the benefit of it being the mirror of it? How does that help you?
We want to work out most of the things. Well,
All right, so
Yes.
what theory would you be relying on, given that it's the mirror, as you say?
reveal that.
What theory would you be relying on, given that it is the mirror, as you have stated? Huh?
Transmission.
All right. No, you're not understanding what I'm saying. But all right. So let's go to Mr. Dixon. Thank you, Mr. Beckford. Dixon, your thoughts?
Well, sir, based off the network, sir, it's a cascade network. So
In a
we would have to
cascade network, how do you define a cascade network?
and two ports are two networks are joined together, sir. In
Huh? All right, Mr. Morrison, talk to me. What would your approach be? David?
Yes, sir. I'm not too sure, sir.
Tell me what you would do. Didn't ask if you're short. Tell me what you would do. So Morrison. Mr. Morrison, we're waiting you. We have all evening. Is it that Mr. Morrison has left the room? All right, so we help him out. So Thompson,
Sir,
tell me what you do. Just tell me what you do.
sir, I would consider trying from first principles to find the hybrid parameters.
So you'd start with the hybrid parameters from first principles. All right, fair enough. Fair enough.
So how would I do that, sir?
Huh?
Continue how I would do that?
No, man, I just want to know what your approach would be. You say you do it from first principles, finding the hybrid. Fine. I just want to hear what's in your headspace. What about you, Mr. Humphrey?
Sir, my approach would be trying to configure the network to get something closer to symmetry.
What do you mean by that? Explain that.
All right, so I'm looking at the parallel branch with the 4 ohms and the 7 ohms. I'm seeing on the other side that you also have 4 ohms and 7 ohms. So I would try to get those resistors, try to get one resistance value for that branch. However, I'm seeing—
You mean combine these?
Yeah, combine them. But
Yeah,
what I'm seeing that if you do it on that side, you would have to consider that 4 ohms is in
Oh,
series.
no, whoa. Mr. Humphrey.
Yes, sir.
It's just don't take this question in the wrong way. You're transferred from the diploma?
Yes, sir.
Okay, all right. All right. The approach that you're presenting would be, I mean, there's absolutely no way you could simply combine these. That would be totally incorrect. But I will communicate with you outside of this forum. All right?
All right, sir.
Sarges, let me hear your approaches.
Sir, if I don't have to split the circuit, I would not have to. I would just use first principles and find the impedance parameters first. Then from that, I would just use the conversion matrix to find admittance and hybrid.
Okay, fair enough. You take on the same approach as Thompson.
Right, basically.
Sir Atkinson?
Yes, sir.
Talk to me. Just tell me the approach you would take.
All right, so my approach would be to break up the circuit from the 6 ohm. So I have 3 ohm on one side and 3 ohm network A, 3 ohm, the 5 and the 4 and the 7 network B, 3, the 4, and 5 and 7. Right?
Yeah.
Then I'll go ahead and find a hybrid parameter for each of them. It would therefore be a cascading circuit. So I add Hold on. I'm gonna find
It's all right, it's all right, it's all right, it's all right, it's all right.
Yeah.
Don't worry. It's not about wrong or right. I just want to hear what's in your head, and then we take it from there. So we're running out of time. We only have 10 minutes left. Let me hear from Mr. Gail. Gail McFarlane and then Powell. Oh, sorry, I skipped Mr. Morgan. Mr. Morgan, talk to us. Linva?
Yeah, I'm after the man just called from my class.
Sir,
Go ahead, Mr. Morgan.
for me, sir, well, we already see you have the 7 and the 5 in parallel on both sides, sir.
But they are not in parallel, Mr. Morgan. You're also coming from the diploma, right?
No, sir.
You serious?
No, sir. I'm coming off a leave of absence. I'm well rusty.
I can hear the rust, Mr. Morgan. All right. Okay, Mr. Gill?
Yes, sir. Well, I popped in the class, but I'm actually balancing 2 classes at once, sir.
All right, so we go to Mr. McFarlane. Mr. McFarlane?
Yes, sir.
Tell me your approach.
My analyzation, I can see 2 pi network that is symmetrical. So I'll try.
Are they symmetrical? They are not. Remember, symmetry means that it's the same network from either port, you know. So if you take for the 2 pi's, yes?
Yes,
they are not symmetrical, but you do have 2 pi's. Go ahead.
Okay, they're not symmetrical because 7 ohms and the 5 ohms are different.
Yeah.
Okay.
So if you have the same values here, then it will be, and the same values here, then you would say you have 2 symmetrical pi. All right. Okay, Mr. Powell, last one on the block for tonight.
Well, sir, the easiest way to me is to so the first I'll split it in 3 basically.
You would put it in 3.
Yeah, because the first network is a pi network. So once you find that one, you find the third network automatically.
Yeah.
Then you find the transfer parameters for the 6 ohms, and then you product them across, and you get the transmission parameters for the whole circuit, and then you do it conversion.
Okay, all right, thanks. Okay, so gentlemen, here is what I want you to do. Here's what I want you to do. If you note, the question did not specify anything about the transmission, right?
No, sir.
So you are seeing admittance, impedance, and hybrid. Now, I want you to, have you drawn the circuit already? I hope you have. I just want you to take the final values. All right, so you're just going to write down the final values because you're going to do an exercise for me. Today is Thursday. I'll give you until Tuesday. It's Tuesday we have class or Wednesday. Next week, Wednesday. All right, I'll give you until Monday evening. All right, so here is what I want you to do. Here are the values. So write this down. Y11, 0.28263. You write that?
Yes.
All right. So Y11 is that. Y21 is 0.032833. Please don't forget the sign. It's minus 0.032833. Bravis?
Yes, sir.
And then we have Y22 328518. And then finally, Y12, right? The same as Y21. All right? So you have these values. So you have the admittance parameters. And these values that I have calculated here are found from first principles. And first principles, remember now the admittance parameters are short circuit parameters. So I'm going to go back up top. So first, I short circuit port 2, and then I find ZT, invert that in order to find Z11, Y11. I then do this voltage division thing, multiple. Remember, once you have the resistance equation and all those values, you are then going to be dividing wherever you have a plus sign. All right? But you would have, I mean, these are things you are familiar with from Networks 1. And then you're finding Vx, Vy in order to find what I2 is equal to. Okay? Note, just some hints I'm giving you here. Because you have a short circuit here, it means that no current will flow through the 5 ohm. So it means that the current will pass, I2 will pass through the 4 ohm resistor. Okay? And you repeat that with port 1 short circuited. So you're now finding Y12 and Y22. All right? Now, having done that, you have now found the Y values. For the persons who suggested that I think the first person I spoke to, I don't remember who it was, suggested that we split this along the 6 ohm. Personally speaking, it could work, but I think the person who was suggesting that really was just following what we did in the previous question, which I have no issue with. However, I want you to then sectionalize the network in 3. Because one of the things you need to begin to appreciate is that with what I just showed you in finding all these values, I guarantee you that it's not as easy if you're not on top of your game. And it will take quite a while. And this is what's going to make the difference between someone who is able to complete the exam within the 2 hours and someone who is going to take 5 hours and still not finished. Let's call this network A, let's call the 6 ohm network B, and let's call this C. As Mr. Powell correctly said, once you have found the transmission parameters for network A, they will be equal to the parameters for network C. Because looking in, you see the 7, and then the 4, and then the 5. So both networks, in terms of going from left to right, both networks are the same. You then have the 6 ohm, and you find the transmission parameters for that. So the overall transmission parameters, and you must do them in the same order of the networks. would be TA, TB, and TC. All right, so I'm going to give you a whole heap of work to do, you know, gentlemen, because it is important that you're on top of this thing, right? It don't make no sense we continue if, you know, I'm getting responses like Mr. Morrison was giving me that him simply no. That don't cut it. And I'm not impressed with that sort of approach. All right? I don't mind if you tell me something that is incorrect. It alerts me to what I need to teach you. Good. So you're going to split the network into 3. And having found T, you're then going to convert T to Y. T to H. Now I've given you the values for Y, so you can confirm whether or not your T is correct. You have your T to Y, your T to H, and your T to Z. So you understand the assignment? The assignment is you're going to do from first principles. Yes, so from first principles, you're going to find the Y parameters. All right? So that's the first exercise, and that is to confirm the values that I gave you earlier.
Sir, just a moment. What if I want to find the impedance and then just do the Y? If I don't want
whatever floats your boat.
Okay. So
whatever floats your boat.
All right.
You're going to confirm the Y parameters. So confirm that from first principles. So if you want to go Z, go Z. All right? I guarantee you it is not as simple. But anyway, so you find Y, confirm the Y values I gave you, and then you're going to break the network into 3, find the transmission parameters for each section, and the overall T. And you convert that T to Y, which you would have confirmed already. You convert your T to hybrid, and you convert your T to Z. All right? And that is due Monday evening. So you have Friday, Saturday, Sunday, Monday. You have 4 days. All right, that's it from me for today. I'll put up the link for this assignment, and then on Wednesday, all things being equal, we'll go through some other exercises. So we'll look back at some of the questions that we have already done and see how interconnection, network interconnection, will make them a lot easier in terms of analysis. All right, have a good evening. Take care.
Good evening, sir.